Last time we were talking about polynomial representations of GLM. These are representations from GLM to some vector space. So, maybe I should write GLM K like this, and this is some K vector space, and the condition on these representations is that their matrix coefficients are all polynomials in the entries of this matrix, right. So, one way of thinking about it is to say that for every linear functional z on V and every vector V on V, this function g goes to the inner the pairing of z on rho g V is polynomial in V. The defining representation, for example, the representation of GLM K on K to the M is polynomial because its matrix entries are just the entries of the matrix, and then you can take tensor powers and you can take sub representations and quotient representations and so on. And what we found is that such representations can be studied through Schur algebras. I had defined algebras S, K, M, N. So, this M is just the GLM M. This N is the homogeneous degree of the representation. A module, this is a Schur algebra, and the modules for the Schur algebra correspond to homogeneous representations of degree n, homogeneous polynomial representations of degree n for this group. That just means that these matrix coefficients are actually homogeneous polynomials of degree n, and every representation of GLMK which is polynomial breaks up into a sum of representations which are homogeneous. So, in order to understand the polynomial representations of GLMK, for example, to classify the irreducible polynomial representations, it is enough to understand the modules for SKMN. Let me quickly remind you how SKMN was defined. SKMN was just defined as the dual vector space of something I called AKMN, and AKMN is just homogeneous polynomials in the entries of the matrix. So, that means in m squared variables of degree n. This is just this is not an algebra, this is just a space, and you look at its dual space, and that can be made into an algebra. The notation I used was that so given alpha and beta in this, I want to tell you what alpha beta is. So, I must tell you what alpha beta does to a polynomial, and the notation I used for that was this. So, this just means the linear functional alpha beta, what it does to the polynomial f. I use the notation of integral, just it is just a formal thing, it does not really mean anything, but it is a nice intuitive notion because it allows you to think of elements of the Schur algebra as distributions, as polynomial distributions on the group. So, I defined the product. So, I must tell you what this is in terms of the action of alpha and the action of beta, and this becomes now G here is GLM K, and this is just by definition f of x y d alpha x d beta y, and I had explained why this makes sense. This is a polynomial in x and y, therefore, you can think of it as a polynomial in y whose coefficients are polynomials in x. You can integrate out those coefficients and you can get a polynomial in y that is the inner integral, and then you integrate that out and you get a element of k. So, that is the double integral. So, this is the definition of the product, and so this is just the definition of the Schur function, Schur algebra. Okay, now let us come down to trying to actually understand what this algebra looks like specifically. So, the basic combinatorial object here I will call IMN. It is nothing but you take the set 1 to m and take its n-fold Cartesian power. AKMN, yeah. Yes, so my thing was I did not want to introduce the notion of a co-algebra. Usually the way it is done is that this is shown to be a co-algebra, and from that you get an algebra. There is no need to introduce a co-algebra. We are all familiar with the representation theory of modules, but yeah, exactly. So, it is worth mentioning that in Green's exposition, for example, there is a co-algebra. But I would also mention that in Schur's PhD thesis there is no co-algebra, there is just an algebra, and he just defines it using formal symbols, which is what I am coming to in a moment. And he does everything, he does not even say algebra, he defines a bunch of operators and how the rules for their composition. So, this co-algebra thing is a rather later thing, which I feel is an unnecessarily introducing a new concept. Okay, so here's the combinatorial object that will play a role in understanding the Schur algebra. I just take the set of numbers from 1 to m and take their n-fold Cartesian power. This is just things of the form, I will write them as I underscores, so they are multi indices I1 up to In, where each of these things is from 1 to m. Yeah, so the dimension of SKMN is just the dimension of AKMN, it is a finite dimensional vector space. Yeah, now I will describe precisely a basis for SKMN, and so this is called a multi-index, and given two multi-indices you can write down a monomial in the n squared variables x I1 j1, x I2 j2, x I n jn. This is a monomial of degree n. I hope it is understood here is that j is the multi-index j1, j2, jn. Okay. So, now this is a monomial of degree n, and you can make Sn act on Imn just by W. So, W is some permutation, it acts on I1 In. W is a permutation of n objects by acting on these indices, it just permutes these numbers I W1, I Wn, that is the action. And I will say that see, these monomials are defined by pairs of multi indices. So, I will say that two pairs of multi indices are equivalent, these are all multi indices, if there exists W in Sn such that W dot I is equal to k and W dot j is equal to L. That means you can find a permutation that takes I to k and the same permutation takes j to L. The relevance of this definition is that x I j and x k L represent the same monomial. See, I could have just rearranged these terms in the monomial and it would still be the same monomial, and this definition of equivalence precisely captures that. So, x I j is x k L if and only if I j I comma j is equivalent to k comma L. That is why I have this definition. Okay. Now define epsilon I j to be, okay, so it follows that the dimension of AKMN is the number of equivalence classes under this equivalence relation of pairs of multi-indices, because that gives you all the monomials exactly once, and the number of monomials is the number of such classes. It's okay? Okay. So, then I will try to give a basis of SKMN, the Schur algebra, and so I will just try to take a dual, but of course, many of these are equivalent. So, I will just take care of that. So, epsilon ij, that is an element of the Schur algebra, by taking epsilon ij x k L, or maybe I should be writing integral x k L d epsilon I j x, right. These are just the same notation, to be 1 if I j is equivalent to k L and 0 otherwise. And this is going to be a basis for the Schur algebra as I comma j runs over a set of representatives for the equivalence classes of pairs of multi-indices. Let me just write that down. Epsilon subscript I j as I comma j runs over the Sn orbits in I m n squared. That means, Sn acts diagonally on I m n squared is a basis of Sk m n. So, now we have got hold of a basis of the Schur algebra. Let us try to see what the structure constants are. In other words, if I take two such things and multiply them, what do I get? So, what I want to know is, if I take epsilon I j times epsilon k L, then I can certainly expand it as C r s epsilon r s. I want to know what these structure constants C r s are. They of course depend on I, j, k and L, but and here I would take a sum over r s in S n mod I m n squared, right. That's the thing I want to calculate. Well, just a matter of unwinding definitions. So, CRS is what I will get if I evaluate this product on the monomial x r s, right. So, it is just integral over g x r s, or maybe I will call it g r s. I want to use x and y later for the factor, but this is a matrix and this is the G is a matrix and this GRS denotes a monomial evaluated on that matrix. So, it is the GR1 S1, GR2 S2, it is that product of entries of the matrix. So, think of it as a monomial function, and so I want to calculate this d epsilon ij epsilon KL G, and that is by definition the double integral of, now I must take x and y two matrices, multiply them and look at the RS, the monomial corresponding to RS, d epsilon ij x d epsilon KL y. This is just the definition of multiplication. Now, this is easily seen to be just by the rule for multiplying matrices, summation over all t in IMN, all multi indices t of x r t y t s. They are just asking that I take the product of two matrices and try to write down the monomial corresponding to the multi indices R and S. Okay, but the entries of that matrix themselves are given by a sum like this, where these are not multi indices with just one single index. If you try to write down the monomial, you will get a sum like this over all multi indices, because it is just a product of the corresponding monomials. And these things, suppose we are just computing the inner integral, this is a constant as far as x is concerned, and this thing will either be 0 or 1. It will be 0 if the pair r comma t is equivalent to the pair I comma j, sorry, it will be 1 if that is the case, and it will be 0 if r comma t is not equivalent to I comma j. So, what you get is that this is equal to a purely combinatorial thing. CRS is equal to the number of t, oh sorry, I want the number of t in IMN such that RT is equivalent to IJ and TS is equivalent to KL. Just this number. Okay, let us just keep this aside for a moment and look at another structure where these numbers appear. Okay, so, these are the structure constants for the Schur algebra. When you multiply epsilon ij with epsilon kl, these are the coefficients of epsilon rs. Okay. Now, I will just look at something slightly different and we will see that these same kinds of numbers appear. So, think of just this vector space Km, the defining representation of GLM, and I will write down a basis just consisting of the coordinate vectors E1, Em. Ei is the ith coordinate vector. Now, look at the n-fold tensor product of this. This has basis, I will denote it by E underscore I, where this I is a multi index, and I will just define this to be EI1 tensor, EI2 tensor dot 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 EIN, where I is I1, I2, IN. And this has this is a representation of Sn. Just by W as permutation, rho is what I am calling this representation of E I is E W I. You just permute the order in which you take the tensor product. Now, suppose T is a linear map, linear endomorphism on this thing. I will use the notation matrix notation. So, T, now I have this basis E I where I runs over all multi indices for this vector space. So, for linear endomorphisms I would have matrices whose rows and columns are indexed by this matrix. So, the notation I will use is that T is T I j, where T I j is the I jth entry of this matrix corresponding to the multi indices I and j. This is just the matrix notation, and one easily checks that T commutes with the symmetric group action if and only if, well, okay, by definition T of W dot E j is equal to W T E j for every multi index j. Okay, let us just calculate what this means in terms of the matrices. Take the ith coordinate of this. So, T, maybe I will do it on a fresh board. T W E j, its ith coordinate is summation T I W j, right, because W E j is E W j. Sorry, there's no summation here, it's just this. And that is how you get the matrix from a linear map with respect to a basis. On the other hand, if I look at W T E j I, T E j will have W inverse ith coordinate. So, I should to find the ith to find the ith coordinate of W dot something, I should find the W inverse dot ith coordinate of this. Right. So, this should be T E j W inverse dot I, but that is T W inverse dot I comma j. So, what you get is that T is an SM endomorphism, that is it commutes with the action of Sn if and only if these things are equal for all multi indices I j and for all W in the symmetric group. So, I can just write that as T W I sorry W dot I W dot j equals T I j for all I j in I m n W in S n. This suggests a basis of this algebra. Define E I j, this will be a linear map. So, I will tell you what its kth coordinate is. So, it is 1 if I j is equivalent to kl and 0 otherwise. This forms a basis for the algebra of such matrices. And it is not difficult after all this to just check that if you take epsilon ij and map it to Eij, this was the basis element of the Schur algebra, this is the basis element of the endomorphism algebra of the n-fold tensor product of k to the m. This is an isomorphism of algebras. And this fact is completely, oops, okay, let me get my m and n right. This fact is completely unconditional on the relationship between m and n. So, what we have done now is we have expressed the Schur algebra as an endomorphism of some representation of the symmetric group. And now we will exploit a general theorem about this kind of situation. I will just state it without proof, it is not very difficult to see. Suppose I have some completely reducible A module rho tilde comma V. A is just some algebra, completely reducible A module. I will be applying this theorem to the case where A is the group ring of the symmetric group, and this is k to the n-fold tensor power of k to the m. Now, if n is yeah, so if n is larger than the characteristic of k, then this A module will be split semi-simple, and whatever I say in this theorem will kick in. Let B be the endomorphism algebra. So, this is just going to be the Schur algebra in our situation. Then B is semi-simple. It will just be a sum of matrix algebras, that is why it is semi-simple. The complete reducibility ensures that. And if I somehow make a list of the simple A modules which occur here, so I will index them by some lambda, rho lambda v lambda is the set of isomorphism classes of simple A modules occurring in rho tilde v. Then for every lambda there exists sigma tilde lambda w lambda, a simple B module such that V breaks up into a direct sum over lambda w lambda tensor v lambda. You should think of this as a decomposition of modules for the algebra A tensor B. What's more is that sigma lambda w lambda, as lambda runs over whatever set we are using to index the v lambda, is a complete set of representatives of isomorphism classes of simple representations, simple B modules. Just by knowing the simple A modules which occur in V, you can classify all the simple B modules. And our situation is exactly what we need for applying this. Therefore, the first thing we need to do is to figure out what are the simple representations of a symmetric group which occur in this Km tensor power n. And now I will assume that the characteristic of K is strictly greater than n, so that I am assured that Km tensor n is completely reducible. So, before we do that, let me just make one observation. Suppose I is I1 In is a multi-index. These are the things that index the basis of Km tensor n. Let us define a subset Sk to be those j in 1 to m such that the jth those j in 1 to n such that the jth index in the multi index is equal to k. Okay, so I will just pick those subscripts for which ij is equal to k. Then this will give a partition of 1 to n. So, I am just taking the subscripts and partitioning them according to what the value of ik is. Okay, so, all the ones for which ik is 1, that will be in the first set, all the ones for which ik is 2, that will be in the second set, all the ones for which ik is 3, that will be in the third set, and so on. That is clearly a partition of 1 to n, right, because everything has to go into some set. Some of these parts could be empty, that I am not too worried about, but what I get is 1 to n is a set partition S1 disjoint union Sm. Some of these things could be empty, and let lambda j be the cardinality of Sj. Then what is the stabilizer in Sn of I? Well, it is just a product of the stabilizers of these sets, the symmetric groups of these subsets. So, it is S lambda 1 cross S lambda 2 cross S lambda m. It is a product of symmetric groups, and if you rearrange these lambda 1 to lambda m in decreasing order, then this subgroup, these prod factors get permuted. It just amounts to a conjugation in the big symmetric group Sn. Okay, so this what this says is that if you take the orbit of E subscript I, then so let us just call that span of E I prime where I prime belongs to Sn dot I. This is an invariant subspace of this n-fold tensor product of k to the m, but this subspace is isomorphic to a very familiar representation when we are doing the representation of theory of symmetric groups. This is called a Young subgroup, and it is a representation induced from the trivial representation of the Young subgroup, or in more without talking about induced representations, it is the permutation representation on the set x lambda, where x lambda is the set of all subsets S1 Sm ordered m tuples such that cardinality of Si is equal to lambda I, and their disjoint and their union is 1 to n. Okay, this is a set on which the symmetric group acts. Then if you take k valued functions on this set, or just take a basis indexed by these sets, that becomes a representation of the symmetric group. And what we are saying is that this index multi index I, it will generate a subgroup a sub representation of k to the m tensor power n that is isomorphic to this thing. And for this thing, from the representation theory of symmetric groups, we have Young's rule, which tells us how to decompose this, right. So, we get k x lambda is equal to direct sum mu less than or equal to lambda v mu, and its multiplicity is a Koska number k mu lambda. I will not go into what this k mu lambda is, suffices to say that it is positive, but let me just remind you what mu less than or equal to lambda means. Mu less than or equal to lambda means that mu 1 plus dot 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 plus mu I is greater than or equal to lambda 1 plus dot 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 lambda I for all I greater than or equal to 1. So, this is called the reverse dominance partial order on partitions. Now, there is only one restriction on this lambda. This lambda, you see this m, this partition lambda, where was it coming from? I had this multi index I, and I used it to partition the set 1 to n into m parts, and then I rearranged those in decreasing order. So, this thing had exactly m parts. When I rearrange them, the parts which are 0 come at the end. If I think of it as a partition, it is going to be a partition with at most m parts. So, the restriction on this is that all these lambdas will have at most m parts. So, we know that lambda 1 prime is less than or equal to m. But if mu is less than or equal to lambda, this is well known to be, we have seen this before, mu prime is greater than or equal to lambda prime, which implies that, just taking this rule for I equals 1, that mu prime 1 is less than or equal to lambda prime 1, which is less than or equal to m. So, the conclusion is that the irreducible representations of Sn which occur in k to the m n-fold tensor power are the v lambdas for which lambda has at most m parts, and all those do occur, because in here there is one piece v lambda where the multiplicity is 1. Let me just write that down, because it is the conclusion of all this discussion. simple representations of Sn occurring in the n-fold tensor power of k to the m are the ones rho lambda v lambda, where lambda is a partition of n with lambda having not more than m parts, which is the same as saying that the conjugate partition has first part less than or equal to m. That's the. So now we are ready to apply this theorem which I had stated a little earlier, because now we know what these things are, and so we know that at least we get classification of the simple modules for the Schur algebra. Okay, we will try to do a little better, we will try to get some understanding of what they are, and this is also work that goes back to Schur. For finite groups, representation of finite groups, we have seen that their characters, at least in the semi-simple case, determine the group, the representation up to isomorphism. If two representations have the same character, then they are isomorphic. Something similar holds for polynomial representations of GLM. But here we can bring into play the beautiful theory of symmetric functions. Suppose sigma w is a polynomial representation of GLM. Okay. Then I will define its, I will call it characteristic. That is a polynomial in variables x1 to xm, and it is just defined to be the trace of sigma x1 xm. Just take the diagonal matrix with diagonal entries x1 xm and look at its trace in the vector space W. Okay, but if you were to interchange two of these, that would amount to conjugating this matrix by a permutation matrix, and what that would mean is that sigma of the permuted thing would be conjugate to sigma of the original thing, and you would get the same trace. And so this is actually a symmetric polynomial in x1, x2, xm. Why is it polynomial? Well, it is polynomial just because sigma w is a polynomial representation. These entries are polynomials. Sorry, I mean if you take any basis of w, then the entries of sigma x1, x2, xm are polynomials in x1, x2, xm. You are adding up certain entries. There is a symmetric polynomial in these things. And our goal is to firstly to calculate these things for the representations w lambda, and secondly to show that they determine representations up to isomorphism, just like for finite groups, under the hypothesis that the characteristic of k is greater than n, the case where that theorem applied. Okay. So, to begin with, let me just prove a little lemma. Let us calculate the characteristic of the representation k to the m tensor power n. Actually, so firstly assume that okay, I will just define some notation. Let p w lambda be the trace of w. This is a representation of Sn. So, w is in Sn on this kx lambda. Since this is a permutation representation, this is just the number of fixed points in x lambda under the action of w, the number of w fixed points in x lambda. Okay, and then the lemma is okay, just for clarity, since there are going to be now two groups acting, there is going to be the symmetric group and there is going to be the matrix group. On Km tensor n, I will look at two representations. One is that of the symmetric group, which I just explained to you by permuting the in the tensor power you permute the tensor factors, and I will call that let me call that rho, and for GLM k, well, this acts by Kronecker tensors on this. I mean GLM k acts on k, so it acts Km, so it acts on the tensor point. I will call that sigma. And here is a lemma which is quite interesting to prove. The trace of these two actions commute, because I just showed that the Schur algebra is the endomorphism algebra of this representation of Sn. And from that, it is not difficult to show that this action commutes, because the action of the Schur algebra is built from the action of GLMK. Okay, or rather, you can recover the action of GLMK from the action of the Schur algebra. I described how to do this in the last lecture, and that process will show that these things commute. So I can write in any order I like. I can either write rho w and then sigma x1. Yeah, so you are saying it is actually quite trivial. Yeah, here I am just coming back to, yeah, that is true. It's quite clear that they commute here. And the trace of this, the character of this, I can write either rho w first, or I can write sigma x1 x2 xm first, does not matter, but this on, let us calculate this thing, Km tensor n. And the answer is that this will be summation Pw lambda m lambda x1 xm, where m lambda is the monomial symmetric function of shape lambda. This is the sum of all monomials in x1, x2, xm of shape lambda. A monomial is of shape lambda if one of the variables occurs with power lambda 1, another occurs with power lambda 2, another occurs with power lambda 3, and so on. If you take all the monomials of that shape, you get a symmetric function, and it is that. And this is a sum over all lambda, I guess. And when I look at monomial functions in m variables, monomial symmetric functions, they are 0 except when they are 0 if the number of parts of lambda is greater than m. So here I might as well assume that I am looking at partitions with at most m parts. So this is the monomial symmetric function of shape lambda. And well, how do you compute the trace of something? Just the easiest way is to take a basis and then look at what each basis vector contributes. We already have a basis. We will take E I, where I is a multi-index, and let us look at what happens when we do rho w sigma x1 xm to this. So, what will happen is that when you do this, then you will get x1 to the I1, x2 to the I2 and so on. So, I will write that as x to the I, that is just x1 to the power I1, x2 to the power I2 and so on, and times E w dot I, because this thing just permutes the multi index down there. So, the contribution to the trace will be 0 if w dot I is not equal to I, and if w dot I is equal to I, the contribution to the trace will be x to the I. So, the trace itself will be, so I contributes to the trace if and only if w dot I is equal to I, which means that the partition, so to I you can associate this partition S1, S2, Sm. It just means that this partition is preserved, the parts of this partition are preserved by W. So that means if and only if S1, S2, Sn, this is of course in x lambda, but I want to say that it is fixed by W. And this is in x lambda for some lambda, but if it is in x lambda, then the contribution is to the monomial symmetric function x to the m lambda. So, it contributes m lambda to the trace if and only if Wi is I and the corresponding, maybe I can just erase this, if and only if S1, S2, Sn is in x lambda W. So, this gives a bijection between the basis elements which contribute m lambda to the trace and which contribute a monomial of shape lambda to the trace and the fixed points of this thing. Okay, so that shows that the trace is just the coefficient of m lambda is this. Okay, so that's one calculation. And now we'll just use some fact from symmetric functions, which I won't prove today. It has to do with various transition matrices between different families of symmetric functions, and it says the following. It says that now here we are looking at symmetric functions in m variables. There is this notion of symmetric functions in very large number of variables, or ideally in infinitely many variables. I won't go into all that, but I'll just those can be specialized to n variables, and the result is the following. If you take the sum over all partitions of n, S lambda, this is a Schur function of shape lambda, and this is where Schur functions will come in through this identity. What is chi lambda W? Chi lambda is the character of rho lambda or V lambda, the representation of Sn corresponding to lambda, the partition lambda at the permutation W. This is equal to the sum over Pw lambda m lambda x1 xm. So, this is again the same expression here. We had proved this in one of my earlier lectures on symmetric functions. I won't do the proof again. Okay, so this is the fact, this is the only fact that we'll use from the theory of symmetric functions. On the other hand, we have this decomposition, you know, let me write it down here. Yeah. So, what I am going to say is that we have this decomposition of Km tensor power n as summation, well, I should write it as direct sum lambda prime 1 less than or equal to m of w lambda tensor v lambda. So, if you take the character, so we calculated the character of the left hand side. What is the character of the right hand side? The character of the right hand side is summation, this guy has character summation chi lambda x1 xm character chi lambda w. So, what we get is that this guy, we calculated though that to be this thing. So, this guy is equal to summation of the characteristic of the lambdath representation and I can just forget about this bit. This was just the intermediate step. So, these two things are equal. Where are they equal? You should think of this as an identity in the group ring of the symmetric group, but not with coefficients in K, but with coefficients in symmetric polynomials. So, let us use lambda Km to denote symmetric polynomials in m variables with coefficients in K, and just take the group ring of the symmetric group with these coefficients. So, both these are expressions in that. This is an element of the symmetric group and these things are symmetric polynomials in m variables, right. So, these two things are equal in this ring. Now, in this ring, well, just think of it as a vector space. The characters of the symmetric group are linearly independent elements. Therefore, if two linear combinations of those things are equal, then their coefficients must be equal. Okay. And here we have got in fact lambda 1 prime less than or equal to m as an additional thing, because we know that other things do not occur here. Okay, so, what does that get us? It gives us a couple of things. Firstly, it gives us the characteristic of w lambda. Which is one of the major theorems. It also gives us a somewhat innocuous fact that if lambda 1 prime, if lambda has more than m parts, then the corresponding Schur function must be 0 when specialized to m variables. Lambda prime 1 is greater than m. You could have proved this using other means, but this is a nice proof of it. Okay. And this I will need in order to conclude that a polynomial representation is determined by its characteristic. See, what is going on here is we have got these symmetric functions in infinitely many variables. I will call them wedge k, lambda k, and I will use n to denote the degree and homogeneous part, and then you have got specialization, which means that you keep only m variables and the rest you set to be 0. So, then you get a symmetric function in finitely many variables x1 up to xm. And what we have is that here S lambda lambda is a partition of n, that this thing is a basis, right. So, its image here must be a generating set. So, this is a basis implies that S lambda, where lambda has less than or equal to m parts, is a spanning set. But then it is not difficult to see, for example, using monomial symmetric functions, that the dimension of this space is precisely the number of partitions with at most m parts. So, this spanning set must be a basis. Okay, I was able to write this here because of this fact that the others just go to 0. So, the non-zero ones must be a spanning set. So, what I get is that the Schur functions S lambda, well, strictly speaking I should write S lambda x1 x2 xm, where lambda has at most m parts, form a basis of symmetric functions of degree n in m variables. So, then from that I can conclude that these things are linearly independent, and from that I can conclude that if two representations have the same characteristic, then they must be isomorphic, because these things being linearly independent, the multiplicities are just the coefficients in their character in terms of these things, and they are completely determined. So, get one more theorem of Schur, that sigma w and tau u, if sigma w and tau u are polynomial representations of GLM with characteristic sigma equals characteristic tau, then they are isomorphic.